Good afternoon, I am Mr. Ish. Thank you for joining me for this video, pH calculations involving strong acid, strong base, where we look at three very important but different scenarios which you have to be familiar with. This is a video, all the material here is direct precursor for the titration questions which you have to be familiar with, which involve weak acid, strong base, or a strong acid and a weak base. In this video, we're looking at everything strong acid, strong base. So let's look at question number 1. Our first question is this: we have 100 milliliters of 0.1 molar hydrochloric acid and you're mixing it with 100 milliliters of 0.1 molar sodium hydroxide. You know you have strong acid, strong base. Always think about molarity is equal to moles over volume. You have a reaction that will be HCl plus NaOH to give you NaCl plus water, but you know you can do a net ionic reaction. We're not worrying about that because I'm here showing you everything in a very relevant and simplified manner without skipping anything, without doing any shortcuts. If you're looking at everything like this, you want to be thinking about moles, and moles is always equal to molarity times your volume, and volume is always in liters. You have 0.1 times 0.1, that'll be 0.01 moles HCl. You have 0.1 times 0.1, you'll have 0.01 moles NaOH. When you have equal amounts, you know everything neutralizes, but we have to mathematically prove that and show that to be the case, because we're not doing any assumptions. You're starting out with 0.01, 0.01, they hit each other, they neutralize each other, and you get water. What ends up seeing, you neutralize it all. You end up seeing 0 here and a 0 here, and you end up seeing this part over here, which is all irrelevant. These things completely neutralize each other such that when you have that water, the product here, it forms and then it goes in a back reaction, or you can have a dissociation and association reaction. You end up seeing H plus plus OH minus. What happens over here? You're basically seeing X here. You have a certain amount over here which is irrelevant because it's liquid, but you end up seeing the water proton dissociation constant for water is equal to here H plus times OH minus, and you know this is always equal to 1 times 10 to the minus 14. I don't know how much these are, but their x square is equal to 1 times 10 to the minus 14. Remember, all of these things zeroed out because you have equal amount of this, equal amount of this. It doesn't matter how much you had in the strength, but they fully neutralized each other out. Hence, we're stuck here in this dilemma, and now we're trying to determine the concentration of hydrogen ion, because we're always looking at pH calculations for all the three examples I'll show you. X square is equal to this. You know this. This is a constant you have to be familiar with. X is equal to hydrogen ion concentration, which is equal to the square root of that, 1 times 10 to the minus 14, which is equal to 1 times 10 to the minus 7 molar H plus. Then you're doing pH is equal to negative log hydrogen ion concentration, which is 1 times 10 to the minus 7. You do that, you run it through, you'll get a minus 7, you'll get here pH is equal to 7. A completely neutral solution because you have equal amount of strong acid, equal amount of strong base. And this completes our fundamental case or scenario type 1, where you have equal strong acid, equal strong base in terms of their moles, and you'll always have a neutral pH solution, and that will be 7, and I've shown you why that is the case. Case number 2, you have strong acid, strong base, but they're not in equal quantities. When they're not in equal quantities, either the acid or the base will dominate, then it will direct the pH based on what it is. If it's an acid dominating, you'll have a strong acid pH. If it's a base dominating, you know you'll have a basic solution, it'll be high pH. We have to convert all of these into moles. We have a start, change, and an end. I have 25 ml 0.1 molar HCl. I have 15 ml 0.15 molar sodium hydroxide. Which one is a higher quantity? Well, multiply them out. Every time convert your milliliters into liters. I have 0.025 liters times 0.1. I have 0.0025 moles. 0.0025 moles HCl, 15 ml and 0.15, 0.015 liters times 0.15, I have 0.00225, 0.00225, which is a larger number, which is a smaller. This is a smaller. If it's the smaller number, the base will fully neutralize itself because it will be overcome by the higher amount of HCl. An equal amount of this will neutralize an equal amount of this, and you'll still have this left over. This amount which is left over will then direct the pH of this overall solution. Minus 0.00225, this will fully neutralize 0 out, but this won't. You will minus these two. Here you'll have 0.00025 moles. You know the pH depends on the molarity. I have to convert this back into molars. I have this equation, moles is equal to volume times molarity. I have moles and molarity is equal to moles divided by volume. This is my moles of HCl. You know, because once this is fully neutralized, you have still HCl, excess HCl remaining, and it'll go through this type of reaction. Now you're determining the concentration of that because that will direct your pH of the solution. Divide this by the total volume. Not this, but the sum of these two. What's 25 plus 15? It's 40 ml, which is 0.04 liters. Divide that by 0.04 liters. I get here a 0.00625 molar HCl, and you're going to do pH is equal to negative log of this value. I'll log it. Then I'll hit minus. I get 2.2. My pH of this solution is going to be 2.2. That leftover acid is a strong acid, so it has a very low pH, and this is a very acidic solution, but you see how everything came about. In these type of questions where you have unequal amounts of acid or base, you have to see which one is more. The one which is more will fully consume the other species, and then the one which is left over will then direct the pH concentration and the hydrogen ion or the hydroxide ion concentration by means of this total volume, which will be existing in that particular system. This is our third and last case. We have 40 milliliters of 0.24 molar HCl. We have 75 ml of 0.14 molar sodium hydroxide. You have to see which one is higher. Very likely this is higher because this is our case 3 where the base has the higher amount of moles compared to your acid. But let's do the calculation. Convert everything here into moles using this formula. Moles is equal to molarity times volume. Convert the volume always into liters. We have 0.04 liters times 0.24 molar. I have 0.0096. 0.0096 moles HCl. 75 milliliters 0.14. 0.075 liters times 0.14. I have 0.0105. 0.0105. Which one looks like a larger number? This is. So this right here will fully consume and utilize this amount, this entire moles over here. So you'll have to minus this from itself, and you'll minus this from here, because the leftover amount of your sodium hydroxide, your hydroxide ions, will then direct the pH of the solution. Here you're having 0.0009 moles of, we'll just say OH minus, because this is the amount which is in excess. It'll have a reaction such as NaOH is going to give you sodium ions and hydroxide ions. This hydroxide ion will then affect the pH of that solution, making it quite basic. The number of moles divided by the total volume, 40 plus 75, which is 115, which is 0.115 liters, will give you the molarity of your hydroxide ion concentration. What is it? You have 0.0009 divided by 0.115. I have 7.826. 7.826 times 10 to the minus 3 molars hydroxide ion. Now I'm going to do this in a different way over here. You can always use a POH is equal to a negative log OH concentration. You can also say pH plus POH. The sum of these two is equal to 14. Therefore pH is equal to 14 minus POH. But I'm doing it in a different way. What is the different way I'm doing? I'm thinking about this. KW, your water dissociation or the proton constant, is equal to your hydrogen ion times hydroxide ion. And then the hydrogen concentration is equal to your 1 times 10 to the minus 14 divided by this 7.826 times 10 to the minus 3. And I'll do that. I have 1 exponent 14 minus your water proton dissociation constant divided by molarity of your hydroxide ions to give you this, the molarity of your hydrogen ions. Your hydrogen ion concentration is equal to 1.277 repeating times 10 to the minus 12. Then you know by means of the negative log H plus, that's equal to your pH. You do the log of this, and then the negative, you have 11.89. Your pH for this solution is 11.89. It's a basic solution because you have more moles of base, fully neutralize your hydrochloric acid. The remainder of this is then what directed the solution to be more basic than acidic. And now you can see how these type of questions come about. Strong acid, strong base questions are not hard, but they're not also very easy unless you do it in a methodical manner and you work everything out without assumptions and shortcuts. I've given you 3 cases where these are equal, you'll have pH 7. A case where this is an excess, you'll have an acidic solution. A case where this is an excess, you'll have a basic solution. In those type of cases, the second and the third case, always remember to bring in your total volume so you can convert the moles of that leftover, either the hydrogen or the hydroxide, into a molarity calculation. From that, you can do your pH calculation. Thank you for watching. Have a good day.